So I think I need your attention, please. We start our lecture. I think let me review shortly what we have studied in the last week. I think student, I need your attention, please. Okay, I think we are talking about the polarization, right? Can you see it? And what we are discussing is that is a linear polarization. Yeah, linear polarization. And in linear polarization means that the state of the polarization is equally. So the polarization is a process. The polarization is a process which approximates a given sample to a given polarization level. So it means that after polarization, we obtain a sequence of polarization level. Yeah. And the amplitude of our polarization level is it's a little bit different to the original one. Yeah. So that's why it's introduced also called like quantization noise. Yeah, quantization noise. And in our previous lecture, we have a review or we have discussed about the quantization noise or quantization error. Yeah. So in this figure, yeah, we demonstrate a nature signal, which we should be approximated by a given polarization level. Yeah. And in this case, we have S. We have a S. It means that we have M is a number of polarization level is equal to 8. Yeah, it's equal to 8. You can write down together with me. Yeah. So later on, I will introduce a given polarization level will be coded to a number of bits. Yeah, and let's say that each of polarization each of level of polarization level is coded by n bit. Yeah, and we have equation that 2 power of n is equal to m. Yeah, equal to m. And in this case, n is equal to 3. Is equal to 3. And m is equal to 8. So we have a 4 level positive and 4 level negative. Yeah. 1 over m is a probability. Is a probability that a polarization level appear. That's the probability because we have a s, or in the general case we have m. Then m or 1 over m is a probability. It's a probability. Probability. That is the curve. These are the dimension of this. That's a probability, and that is the amplitude. Okay. So if we want to calculate the collision noise or collision error, we need to make a difference. Make different. That is collision error. That is the signal after polarization. Signal after polarization. I think in all of this concept lecture I have discussed very detailed in our previous lecture. after quantization. That is a signal after quantization, and here is a original one. That original signal. That is original signal. Okay. So that we have discussed is very clear in the last line. And observe the amplitude of the quantization noise. So we will see that the maximal, that is maximal amplitude of the quantization noise. Maximal amplitude of quantization noise. So because we assume that the signal is equally distributed from the maximum amplitude and to the minimum amplitude of the quantization level. Yeah. So it means that it's equally distributed in this area. So in this case, that the noise is also equally distributed in this area. This is Q. Minus, that's the lower bound is minus Q over 2, and upper bound is plus Q over 2. So the probability, the probability density function of the noise, the PDF of the noise, PDF, that's probability density function of the quantization noise is 1 over Q. Okay, so let me move so that you can write. That's PD. This one. This one. That's probability of the noise 1 over Q, because the noise is equally distributed from Q minus 1. Q over 2 minus Q over 2. Resultant bliss 2 plus Q over 2. So in this case, that the probability of the noise is 1 over Q. That's the first probability, probability of the quantization noise, and that is the probability of the quantization level. Okay. The PDF of quantization level. So that I think I have explained very clearly in our previous lecture. Just really will be. So now we calculate the signal to quantization noise ratio. And the definition of the signal to noise quantization ratio is defined by the average power of the signal. That is average power of the signal. Average power of the signal. That's the first one. And here is the average power of the noise. Average power. That's average. Averaging. That's the similar definition. That average power of the noise. Average power of the noise. Okay. So based on this definition, we calculate 18. The first term, that's the noise. So here I give you a final. I have the final equation, but actually you can also calculate it by yourself. So you have that integration of the lower bound is minus Q over 2. And the upper bound of the noise is amplitude, Q over 2. Okay. And because we should take the power of the amplitude, so we need to take the square of amplitude, that is square. And we need to multiply with the probability that the noise appear that we have discussed in the last week, 1 over Q. So here, that is a integration variable. So here, mathematical we can define very easy, right? That is 1 over 3. Yeah. X cubic is a, I'm sorry, I made a mistake here. Square cubic, I'm sorry. Yeah. What is this? So I cannot move. That is up about is Q square, and here is a minus Q square. I'm sorry, Q over 2. And probability is 1 over Q. Okay. So if you are doing this calculation, we obtain this one. Yeah. It's very easy. We obtain the noise power of the position noise. So that is the what we did in the last week, and what we can do also this one. Yeah, that is a signal power, and we do the signal power this one. Yeah, that's the final result. But you can do it by doing a summation. Yeah. So because we do this summation, because we have the two part, upper part and the lower part, they have the same energy. Yeah, the same energy and the same power. So we calculate the upper part. I'm sorry. That's it one. So it's from the first one to the last one. Yeah. The first amplitude is let me do it for the strong. So we two is a two because we do only one part. Yeah. First lower part and upper part. We don't forget to multiply with the probability 1 over m. And the first term is Q over 2. And we take this square. Yeah? Square. Okay. And that's by skip. Plus. I'm seeing something wrong here. Plus. The final one. That's student. Pay your attention. Yeah. The final one is this one. That's m minus 1. Yeah. Okay. Q is k over 2. That's the final one. Is case. Okay. So we do it in the last week, right? So we just replace that's the final one by m minus 1. Yeah. Over 2. Okay. And Q. Okay. And again square. That this equation is the last week we have a right already. Yeah. Okay. So please calculate this equation, and that's the final result. The final result. Yeah, so I think that's the equation that we can calculate the signal, the noise power, the signal to noise, the signal to position noise ratio. Yeah, and replace the term what we have obtained for the signal power, and also the noise power. Yeah, so we obtain the calculation of the signal to position noise power ratio. Yeah. So it's equal to m squared minus 1. Yeah, because we take this term. This term divide to this term. Yeah. So we obtain the final one is m squared minus 1. M is a number of quantization level. M is a number of quantization level. Okay. So there's other relation. So M is equal to 2 power of n. And n is a number bit. N is a number of bit used to code a sample. Yeah. You get my point? Okay, so it's very clear. And there's one scale we call the dB. And dB, if you convert the power to dB, the power we will convert to dB. Yeah, then we need to 10 logarithm push. Write down, please. 10 of power of B. That's the power. So if we are convert to the dB, yeah, then we need to take 20. Yeah. So that we have discussed in the last week, and now our lecture in this week. Yeah. After doing quantization, that is original, that our signal. Analog signal. That is this one. And the signal is after quantization. That is this one. That's a signal after sampling and quantization. So about the sampling, we have studied already. Yeah. Don't forget the Nyquist sampling theory. Very important. One of the major knowledge of our lecture is of the sampling theory. Yeah. So I have again review for you. Yeah. What is important? Why we need to follow? So I suppose that you don't forget. Yeah. So that is signal after quantization. And now we need to convert to that is signal after sampling, and that is signal after quantization. Yeah. Signal, that is a signal after sampling, and that's a signal after quantization. The signal after quantization. After quantization. That's this one. So in the final our final result, we need to convert the signal after quantization to the bit stable, because the computer yeah understand about the bit. So you are working with MATLAB, right? MATLAB and C and so on, the high level, we are working with the bit. Signal processing, we are working with the bit. Yeah. 0, 1 and 0, 1. Yeah. So we need to one other step that we need to convert the quantization level to the bit. So suppose in this case we have a S level quantization level. It means we have a n is equal to 3. Yeah. So in 3 we can see that we have a 0, 0, 0, 0 is one level. Yeah. 101 or 1001 and so on. And here also, you get also we have a 4 level upper and 4 level lower, and depend on the quantization level, we will convert this quantization level to a corresponding code word. And each code word in this case consists of 3 bits. So that's the final one. That's the second one that which the signal will be transmitted. So you see that, student, you see that that's the original signal, analog signal, right? And now the computer signal. That's the computer signal. I call the computer signal, but actually that is sequence of bit. Sequence of bit. Or we call that is the computer signal. That's the computer signal. Okay. Here is a human being signal, or original signal. I say human being signal somehow strange. Somehow we cannot understand something we cannot. The voice signal we understand. But the other signal we don't understand. Okay. And here's a computer. It's a computer. So we are happy with one. The computer happy with the second of bits 0101. Computer very happy. So if we put the nature signal to the computer, that's not, we cannot process it. You cannot, the computer happy with the bits second. So I think now you see that is we have studied how to convert the signal to the from analog to the, we have how to convert signal from analog to the digital. Very detailed. And it means that the signal, original signal is original signal. That is the signal in analog form. And we need to do a sampling. Need to do sampling. And then we need to, you can draw it with me, We need to quantization and coding. So in this position, we have a bit 7. Okay, that's a bit 7. So in there is some part that we study in my next lecture. Namely, we discuss about the modulation. But at the time being, we forget about it. We don't discuss it in detail. And after the modulation here, we study in the next chapter. We can transmit signal to the channel. Other channel. Okay. The channel is a medium that we use to transmit the signal. How to transmit the signal, I will discuss this in more detail later, our lecture. Okay. But you know that I'm talking here. Yeah, that's my microphone. Yeah, that is a receiver here. This signal we do not convert to the digital. So that is actually that is FMs, transmitter and receiver. But you know that in somewhere in this room we have a antenna, receive antenna. So we use the waveform transmission to bring the signal from the transmitter to the receiver. So that's a channel. Yeah. So if the channel they have a student, yeah, the channel will study more details in my next lecture. But you know that in the channel they have a noise, you know. So you are discussing, you make noise. So I'm doing like this, you make noise, and keep noise. Yeah. There's some problem with the transmission. I will not discuss in detail, but you know, here's the channel. Yeah, the channel will make noise. But in our lecture today, we don't discuss about the noise channel. So the noise adding to the channel. We just discuss about the noise what we have made as a transmitter. I suppose that you need to listen it carefully. Yeah, in order to understand my lecture. Yeah. So what we have what we have a made noise as a transmitter. Can you tell me what we have made so far? What we have made noise as a transmitter? The first of all, yeah, actually, the first of all, when we do sampling, and depend on the method of sampling, yeah, nature of flat puppet, we make somehow noise in this position. Okay, but we ignore this noise to simplify. We don't discuss about this noise. But the noise that we have discussed, in this lecture. That's the quantization noise. That's the quantization noise. That's the first kind of noise. Write down, please. That is quantization noise. There's noise. Okay. That is noise introduced at the transmitter. This noise is introduced at the transmitter. Yeah. So we ignore the noise caused by the sampling methods. There are some noise there, but we don't make the things too complicated. It makes your headache, yeah, and confused. So I don't discuss it in detail. Yeah. Okay. Is that clear? Student, is that clear? It's clear, right? The first kind of noise is a condition noise that caused by channel. The second noise, that I don't talk about the noise caused by the channel, but the channel makes some noise, but we don't discuss about the how is the level of the noise caused by channel. But we discuss about the arrow. The arrow made by the receiver. The arrow made by the receiver. Yeah, pay your attention, please. Arrow made by the receiver, namely decoding arrow. Decoding arrow. What is a decoding here? What are the decoding here? Yeah. decoding here mean, yeah. So we transmit the, let's say that we transmit the 001, and we transmit the 001, right? To the channel, over the channel. That is channel. Okay. We have a channel. I'm sorry, I make it. And the channel make noise. So we obtain the 101. You get a point? So in this case, yeah, in this case, so we have a 1 arrow here. That is an arrow, right? Arrow. Can you write down, please? We can call that is a transmission arrow. Okay. Make a noise. And this is also the noise. It's a noise. It can be calculated by the noise. Okay. Understand? Got it? Oh, what's happened here? Okay. That's the noise. Yeah. Student, pay attention. That's a noise. The noise caused by the channel, but not we observe only as a channel receiver. Student, now as the receiver, we calculate the signal to noise ratio totally. Totally, yeah. Student, yeah, pay attention. We calculate the signal to noise ratio at the receiver totally, including two effects. The first is condition noise, and second is decoding error or the transmission noise. Yeah. Okay. I hope that you are trying to follow my explanation. Yeah. So we have calculated this one. Yeah. This is different to the first one. In this one, we just calculate only the noise power. We don't care about the channel. Yeah. But in this position, we calculate together the noise, condition noise, and the transmission error. And it called also a noise at the receiver. We call that is total noise to signal to noise ratio at the receiver. PE is a probability that one is error. PE is a probability for that one bit is error. Okay. It's one bit error. Yeah. So much more clearly. Okay. It's a probability that one bit error. PE. And now we calculate all together. Yeah, write down and draw. Yeah, don't miss any information from my slides. Yeah. Did you finish? Okay, let me after understanding all the concept in this slide, yeah, so I move to the next slide. I just underline we are going to discuss calculate the signal to noise ratio totally at the receiver, not at the transmitter. Yeah, under the region of the channel. Under the if the presence of channel or the transmission error. Yeah. And don't care much about this one. Don't care much about the modulation and demodulation. So we will discuss this later. Yeah. I suppose that in the project there's some project already I given already. So you are working on it. Later on we are discussing about it. So we calculate the signal to noise to other receiver as I mentioned before. Yeah. Yeah. So what is it? Sorry. So I write here that is S and R in general. Can you write down please? S and R in general equal to S and R. Yeah. In general, other receiver. Yeah. That's the other receiver. Yeah. Equal to PS. Okay. Over the we have a let me check. That is CQ squared. Yeah. PN. Let me write PN. Write down follow my writing please. And equal to PS. PN there are two parts. One is the P. I think we are this one, this term, yeah. This term. C square V. V averaging. Yeah. And plus write down please. C E student, yeah. D square. Okay. Drawing is not good. That's it term. That's it term. Okay. What is PS? I'm sorry. I'm thinking. Signal power. My power. And sorry. Yeah, right now, please. Yeah. Very good methods. Yeah. Yeah. Dn. ds over c square over c. C square q over c plus c square de over c. I just need to find that follow my lecture. My lecture. So you're putting together, back software. So let's try to follow and then I'm staying here. I'm staying here to play when I go. So you will miss my lecture then. At home, then no one will stay for you. Okay. So we have here is a signal power. And we have here is noise power. Noise power, signal power, and noise power. So now noise power consists of two terms. Two terms. The first term is the noise power consists of two terms. Change color. So this first term is this term. That is a quantization noise power. This term, yeah. That's this term. And the second term we call that is misdecoded noise power. Call that a misdecoded. Noise power. So that these two noise power, so the background is totally different. Yeah. The one is caused by the quantization, and the other one caused by the channel. Yeah. The totally different concept is different. But we adding these together and we call that is a noise power in general. And that's defined by Pn. Yeah. Okay. So now we observe this equation. Suppose that we use an n bit to decode the signal. N bit. That's the number of bit. Yeah. The bit number. We have already the relation m is equal to 2 power of n. Yeah. M is the number of quantization level. Yeah. And we let's say we have a n1. No, I'm sorry. I'm sorry. I don't write m1. B1 make confused. B1. Can you write down, please? Dot B N. Right? You get a point? So if we using the n bit from B1 to Bn, yeah. So we can code. We have a foreign code word. Code word. 0 dot dot 0. That's the first code words, and so on. You can call that is let's say 1 dot, let's say code 1, and here is 0 dot 0, and we have a 1, the final one dot 1. Okay, the number of code word is 2 power of n equal to right. And here is we can denote that is one code word. That is one code word. That is the first code word. Okay. Code word is in Vietnamese từ mã. No. So now we are transmitting this code word. Okay, we transmitting this code word. We transmitting this code word. That is T. That is transmitter, and here's the out. You get a point? It's the same in color. Let's say the receiver. Okay, we have a B1 and B1. Click dot VN strict. So if we transmit a code word as a transmitter, student listen. Yeah, and we receive this code word, and this code word hopefully error. They make an error somewhere. Yeah. So suppose that we obtain 0 dot. Unluckily, yeah. I suppose that is a error. Let's say there's other color here. 1. Oh, so this is error. That's it, error. Okay, that's error. Error. Okay, that's error. And the amplitude of the first error is Q. Write down, please. Amplitude of the first error is Q. Okay. Suppose that we don't make the life so complicated. We make the life more easy for calculation. Student, yeah. Student, listen. Pay attention. Yeah. We send 5 bits, and we suppose there only one is error, and we are calculating the power causing this error. We don't calculate for the more complicated case. That means that there are some other case that is 2-bit error, 3-bit error, 5-bit error, totally error. Yeah, but we don't calculate. We make the line more simple. We calculate only one case. The only one is error. Okay. And the probability of this bit error is PE. That's probability of the bit error is P. It's a probability of this the bit error. Okay, right? And the probability that its P1 error is similar to the probability that P2 error, and so on. Is also equal to the probability that Pn error. Yeah. So it means that the error is or the probability when one is error is the similar to all other case, all case. We don't distinguish the B1, B2, and B3 or Pn and so on. Yeah. So suppose that the bit zero as a second bit error. Yeah. We are discussing the first bit error, but if we are suppose that the second bit error, then the amplitude is 2 multiplied with the Q, because the weight factor of the second bit is 2 times of the first bit. Yeah. So we have the weight factor from B1 to Bn, and the last one, the last one is the weight factor will be 2 power of n minus 1. That's the first weight factor, second weight factor, and the last weight factor. The weight factor relating to the amplitude of the signal here. The amplitude here. Okay, it's using to code the amplitude. That's why we have a difference in factor. Okay, now we need to summation of this all. Cn, C2, C1, C2, Cn, and don't forget to take the student. Don't forget to take the square, because can you answer my question? Why? The power, right? We are calculating the power because we are calculating the power, right? So we need to take the square. So can you write down this equation? Write down. Now write down. Yeah, not drawing like me. Yeah, and write down to understand where it comes from, why we need this factor, and where it comes from. Each element is this summation. Where it comes from. Can write down please. To understand how we calculate the error, the power of error caused by the misdecoded at the receiver. Yeah, write down please. Yeah, write down please. Write down. Yeah, write down please. Write down calculation. That's okay. Oh, you text the note from other person. We need to write by yourself. Yeah, it's nice, but we need to write out. Yeah. Write out and make some slides on notebook. of calculation, full of calculation. Okay. You know which time we need to solve. Okay, so you finish writing? Please, yeah. Okay, so I think after understanding this equation, so I think I give the final results because the last one is a mathematical calculation. Yeah, the last one is mathematical calculation. The P remain. Yeah, so this summation, this results got by this one. Yeah. This one. Yeah. So can you write down the final results? And you can also, okay, this one I make small explanation for you. Yeah. I think in your project there's some very excellent project. You know, there's some projects very interesting. Yeah. So please work on the project to have more understanding about UHC, ADC, and so on. Yeah. I will upload the manuscript of the proposal market short file. Then he's going to give lecture. Proposal market. Okay. So I will upload this manuscript on T. You can download and revise. So after I finish my part, we go come here. We will record and organize seminar with me. From we will start when more detail when we are approaching it. Yeah. Okay. So I think let's say we discuss about this equation. Yeah. So we have defined. Yeah. We have defined. We have defined S and R. I'm sorry, S and okay equal to ds to dn. Okay, that we define already. Yeah. And equal to ds over to c q where everything plus that we define already, right? C d where everything. So this term we calculated already. Yeah. Equal to q square, right? Over 12. Do you remember? Do you remember? Q square over 12, right? And this term is this is quantization noise. Yeah. That's quantization noise. This one. That is a m square minus 1 over 12. Yeah. M square, right? Minus 1. Write down please. Slowly, carefully. On the one is q squared. Right? Plus. I will not rewrite this in no place, right? So is that's right, this term. Yeah. Replace this one. That's it one. Can you? Can you? Right. So here, that's the signal power. Yeah. Here is the noise power. And that means signal power we did already. Yeah. Good. That is the quantization by power. We did already. And that's a noise power caused by the misconduct at the receiver. We did already. Right. So please replace all this results on the equation. What we have obtained before on the equation. That's not replace. Yeah. So if we replace all, and then let's q square, then you obtain the final one. So if we replace all and select the q square, we obtain the final one. This one. That's the final one. The next one is similar to the first one, but then replace n square minus 1 by exponential variable. Yes, student, right? Yeah. At least one yeah, right. It's quite yeah, yeah. I think that's quite similar, right? Because f square minus 1 is equal to signal positive variable. Please, right now. But we are doing it. You are doing exams. But the exam on which is something. Good. Make one lecture. One lecture stuff is simple enough. Yeah. So okay. So if we replace the equation that we obtained in the previous slides, then we replace on this equation, then we obtain the final one. And don't forget the sum following student. Don't forget the sum following relation. Yeah. First of all, m equal to 2 power of n, right? N is a number big. M is the level, is the position level, student. Right? Don't forget. Second one, m square minus 1. Yeah. Is equal to f n q. Signal to quantization noise. Student, signal to condition noise is a noise that we calculated at the receiver. Clear? It's caused by the condition noise. The condition make noise because of approximation noise that we calculate at the receiver. And this term, yeah, this is the at the transmitter. I'm sorry, that is the transmitter. I'm sorry, at the transmitter. Okay, this term, yeah, is actually caused by the channel transmission error. You get the point? But we transmission error. Okay. And this term, student, we calculated totally at the receiver. Yeah. At the receiver. Totally. So we add these two terms together. Okay. So if we are discussing about the signal to noise ratio, so we need to distinguish which place, which region, where it come from. Yeah. So that is the quantization noise ratio. This is total receiver. And PE, what is this? Probability that one bit error. Yeah. Probability that one bit error. Okay. I'm recording. You can watch it again at home. Yeah. So if something is not clear, so you can check again. Yeah. Okay. So that is the end of our lecture. Yeah. We are regarding calculating the signal to noise ratio at the receiver. Yeah. There's some project I think is very interesting for you. Yeah. Very, very nice. Yeah. That we are working with the IDC. Yeah. So you can gain a lot of things. Very interesting. Yeah. It's time again working with I love certain designs. I love mala. I love filter. I love XC. Yeah. That's it. That is some very interesting topic. You are working with server design. You are also working with the MCU. You are working with MATLAB. You are working with the filter design. Everything. That's very, very interesting. Yeah. Very close to the particular application. Yeah. Even regarding this project, you can working also with IoT. So we can you can send the signal somewhere, convert the signal from analog to digital using MCU to connect to the computer. And you can work also a little bit with protocol to transmit to the server. Even you can work a little bit with software application to program a user interface. A whole project, very small project, very interesting. You can learn a lot of things. You are not so boring with particular calculation. Very. So let me let you have a short break.